I'm going to start this by redoing a calculation that we did yesterday, this time with the correct value of the Bohr radius. I just kind of rounded it off when we did it in class. But we have the Bohr model of the atom, and the electron and proton are treated as very small point particles, separated by the distance you can see here. Each of them has a charge of magnitude 1.60 times 10 to the minus 19th coulombs, with the electron having negative charge and the proton positive charge. And in the Bohr model, the electron was treated like a planet orbiting the sun, where for a planet there's an attractive force between the sun and the planet, the gravitational force, which depends or decreases inversely with the square of the distance. And that's the same thing that the electric force does. It decreases inversely with the square of the distance. And so maybe charged particles would orbit the nucleus of an atom, the positive nucleus, the same way that planets could orbit the sun. So let's see how we did. Excuse me. When we did this in class, we calculated the force, and it ended up being, it's an attractive force because they're opposite charges. It's K times the charge of the electron times the charge of the proton divided by the Bohr radius squared, and I'm just putting a little subscript on there. By the way, your book puts a subscript of E on the K, and they make note of K sub E actually equaling 1 over 4 pi epsilon naught, and the subscript is to distinguish it from other K's like spring constants and Boltzmann's constant and things like that. So we'll just go ahead and write it this way. Now, we're just calculating the magnitude of the attractive force, and the charge on the electron is equal to the charge on the proton in magnitude, and that's that 1.60 times 10 to the minus 19th coulombs. And the coulomb is the fundamental unit of charge. Okay, so we did this in class the other day, just plugging in all the values here, but I'll write it down once. 8.99 times 10 to the 9th Newton meter squared per coulomb squared. That's the value of 1 over 4 pi epsilon naught, or the K sub E. And then since we've got the same charge twice, I'm just going to square them. Square it. 1.60 times 10 to the minus 19th coulombs squared. And then that Bohr radius, 5.29 times 10 to the minus 11th meters, and we square that. So unit-wise, I always like to check those out. If I concentrate on what's going on with those, we've got the constant Newton meter squared per coulomb squared, multiplying, when we square this, we get coulomb squared, and then on the bottom we'll have meters squared. And you can see the coulombs squared divide out, meters squared divide out, and we'll end up with newtons, which is what we expect for a force. And when we did this, we got 8.22 times 10 to the minus 8th newtons. And so that's how that one works out. It's going to be important to keep track of units in electricity and magnetism, because there are going to be a lot of units floating around, and it's difficult to keep track of all of them. And so that will be important. Okay, and then calculate the gravitational attraction between the electron and the proton. We also did this the other day. This is just using the gravitational force law. And I guess we could put an F sub g down here. It'll be g times the mass of the proton, mass of the electron, divided by, again, the Bohr radius squared. And when you plug in these numbers, mass of the electron here, mass of the proton here, universal gravitational constant, 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared, and then that Bohr radius, you will end up with units of newtons again, and this ended up being 3.63 times 10 to the minus 47th newtons. And so you can see this thing is many orders of magnitude smaller than this one, like 10 to the 39th times smaller. And gravitation is a weak force. The only way to make it appreciable is to have a whole bunch of mass. All right, so there was that part of it. Then I go a little bit farther with this. I may have had you calculate this in class, or we may have done this. Calculate the acceleration of the electron. This is just using Newton's second law of motion, F equals ma. Magnitude-wise, this is the net force, of course. But in this case, the net force for all practical purposes is the electric force, because gravitation is so weak. Or the acceleration is just that net force divided by the mass of the electron. And so we'll take our 8.22 times 10 to the minus 8th newtons and divide by mass of the electron, 9.11 times 10 to the minus 31 kilograms. A newton is a kilogram meter per second squared. So if you divide by kilograms, you just get meters per second squared. And you get a fairly large acceleration here. It ends up being 9.02 times 10 to the 22nd meters per second squared. So quite a large acceleration on the electron there. In fact, that if a human experienced an acceleration like that, it would turn us into a puddle pretty much. We are not designed to withstand those sorts of accelerations. Okay, and then the last part that I have people do is, assuming the electron is traveling in a circular orbit and the acceleration is entirely centripetal, calculate the speed of the electron. Well, this is pulling in something. Actually, this is something that you did fall quarter, but so is this. The centripetal acceleration is v squared over r for an object traveling on a curved path. And so you can solve for the speed. It'll just be the square root of the acceleration times the radius. And in this case, we've got that absolutely enormous acceleration, 9.02 times 10 to the 22nd meters per second squared times the radius, Bohr radius again. I should put a little r sub b down there. 5.29 times 10 to the minus 11th meters. Looking at the units under that radical, we've got meters times meters per second squared, so we'll have meters squared per second squared. When you take the square root, you get just plain meters. And you end up with a speed here of a pretty good clip, 2.19 times 10 to the 6th meters per second. That's not quite a relativistic velocity. Actually, it would be noticeable depending on how precisely you're able to measure the speed. You may learn about special relativity at some point, but it's going about 0.7% of the speed of light, and that's not an unusual speed for an electron. Actually, an electron in the old style of TV sets with the cathode ray tubes were going faster than that, and so not a terribly unusual speed for an electron. Okay, that's looking at an electron and a proton, where you have a single positive charge here and then a minus charge over here, and you look at the force between them. So far we've only been writing the electric force equation as a scalar equation, but it can actually be written as a vector equation, and should be. Let's suppose we have a charge 1 sitting here and a charge 2 sitting over here. A way that we could write the force that 1 exerts on 2, and I'll just write it as F12, is going to equal K Q1 Q2 over R12 squared, and R12 will represent the distance between charge 1 and charge 2, and we'll be treating them as point particles, so we're not going to have any expanse of them here. But that's still a scalar expression on the right side. I'll have to have an R12 hat, a unit vector, to turn that into a scalar or a vector equation, and the direction of that is along the direction that connects the two things. It's a unit vector. It has a dimension of 1 or a length of 1 and just direction to it, pointing in that direction. Now, this takes care of all the possible combinations of charge that you might have for Q1 and Q2. If Q1 and Q2 are both positive, then their product will be positive and they'll repulse each other, and this expression will point in the direction of R12. If one of them is positive and the other one is negative, then their product will be negative, and when you multiply a vector by a negative, it reverses direction, and the force on 2 will be back in this direction. If they're both negative, negative times negative is positive again, they'll repulse, and you'll be pointing in that direction again. So this takes care of both or all the possible situations having an expression like that. Now let's toss in a complication, and the complication we'll look at here is to start adding more charges. But I'll start with just one charge here, and I'll call that one Q1, and I'll be interested in the force on a charge Q that's out here in space somewhere. I'll just stick its label up there because I don't want to get in the way of some things I'm going to add to this. So just considering that one, we would have the force on charge Q. This would be F. I'll just leave it as an F. It'll be K Q1 capital Q, whatever its charge happens to be, divided by R12 squared, or R1 squared, I'll just call it that, and it's the distance from Q to charge 1. And then I'll have some R1 hat here that I'll introduce. Okay, and so I'll draw the line between these two, or at least a dashed line between them. And R1 hat would point in that direction, unit vector out there. And this length right here is going to be R1. Well, what if there's another charge out here somewhere? Like up here, we could have a Q2. Well, the net force on Q due to these two charges, I'll have to add in the force that charge 2 exerts on it. So I'd also have K Q2 times capital Q divided by R2 squared, and the direction of that force will be different from the other force. So here's my R2 right here, and the direction that one, the unit vector for that one, will be right here, R2 hat. And so And if I've got some other charge here, like maybe here's where charge 3 happens to be, I'll do the same thing. I'll have an R3. That's the distance between charge 3 and charge Q. And I'll have an R3 hat here that has to get added on to those other charges. So this will look like that. KQ3 times Q over R3 squared and R3 hat. And in general, I'll just have to keep going. Now, you can shorthand notation this thing, and eventually you may, if you've got a whole bunch of charges, you may do something like you'll use summation notation. And I don't know, I hope you've used this before. This is a way of signifying a sum, and maybe you've got n charges. You'd have an index that goes from 1 to n. You'd have a k q sub I times capital Q divided by r sub I squared and then r sub I hat. And this could be really complicated. It's bad enough for 2 charges. I'll do an example with 2 charges. But if you have a whole bunch of charges, you'd just go crazy dealing with this, and you'd probably want to write a computer program that would simplify it for you, that could just loop over the number of charges and take all that stuff into account. But if I just went from 1 to 3, that would equal this expression right here. And so that's what the summation notation means. All right, well, let's do a problem that actually does deal with a couple of charges and see how that works out. And this will give you some practice going back to things from first quarter with vectors and angles and all kinds of things like that. So in this case, we have just protons. All these black dots represent protons. We have 3 of them. And we want to calculate the net force on P3 due to P1 and P2. So we'll just have a pair of forces that we have to calculate. But I look at the diagram here. It's got an X and a Y axis, nanometers on both of these. So I'll have to make sure that I take that into account at some point. This P3 is down here. It's 3.00 nanometers below the x-axis and out 4.00 nanometers in the horizontal direction. At least I tried to make it that way when I made this drawing. And so I'm going to draw the forces huge on here because I want to make it easier to deal with some angles and things. So this would be the force that 1 exerts on 3, and I'll just call it F13, like that. And the angle that it makes with the horizontal will be the same angle that a line from P1 to P3 makes with the horizontal. And I'll be calculating that angle here at some point, pretty shortly actually. Now the force that P2 exerts on P3 is just going to be straight down here. It's going to be in the minus j hat direction, and it'll be larger than this one because P2 is closer to P3 than this one. So this will look maybe approximately like that. This will be the force that 2 exerts on 3. And so pictorially, that's what this is going to look like. Whoops, I measured or drew a wrong angle on here. Oh, actually, no, this one is just fine. That is the angle theta. This will also be the same angle. Theta here, and this will also be theta. Those are kind of similar triangles type things. And I may as well calculate it now. Theta will equal the inverse tangent of, there's a little right triangle right here, and it has This side here is 3.00. The horizontal side here is 4.00. And I think that makes it into a 3, 4, 5 right triangle. But the opposite side is going to be 3.00. And the adjacent side will be 4.00. And when you calculate that, you end up with a value for theta of 36.9 degrees. I'm in degrees mode on my calculator, by the way. I'm guessing maybe you've discovered that when you go from physics to calculus, you need to change your calculator from degrees mode to radians mode. I discovered that when I took physics. I had calculus right after physics, and I remember going into a calculus test one day right after a physics test and forgetting to put my calculator in radians mode. And I think this was second quarter when you were doing integrations and things of trig functions, and my answers were not working out the way I expected them to. And with about 5 minutes left in the test, I realized what the problem was. Oh well, such is life. All right, well, let's calculate those forces. These shouldn't be too bad to do, actually. First, I may as well do F23. That's the easy one. Oh, by the way, I just calculated a positive angle here. I know which direction the force is pointing, and so I know this, actually both forces are going to have negative components in the y direction, but I just deal with positive angles. It's better than trying to remember what the domain and range are on my calculator for the trig functions. So anyway, F23 in magnitude will be K sub E times, actually, the charge on 2 times the charge on 3 divided by the distance between 2 and 3 squared. Now, everything in this problem has the same charge. They all have a charge of plus E, and so Q1 equals Q2 equals Q3 equals E, and in this context, E is not 2.71828 ... whatever. It's always going to be 1.60 times 10 to the minus 19th coulombs. And if you want more sig figs, you can keep a 1.602, or you can look up on the board in the front of the room and use half a dozen significant figures if you want, but they're usually useless. So anyway, we'll have 8.99 times 10 to the plus 9th Newton meter squared per Coulomb squared. I was thinking of Q instead. Both charges are the same, so 1.60 times 10 to the minus 19th coulombs squared. Hope that's still showing. Yep, looks to be. And then the distance between those two is 3 nanometers. So this is the point at which I will replace the n for nanometer with times 10 to the minus 9th, and then I've got meters. So, and I have to square that. So that's what we get for F23. And it ends up being 2.56 times 10 to the minus 11th newtons. So we've got that. Now for F13, do the same sort of thing. F13 is going to equal KQ1 Q3 over R13 squared. And as far as the distance from 1 to 3, again, 4 this way, 3 this way, that's a 3, 4, 5 right triangle. This diagonal distance is going to be 5.00 nanometers. So that's the distance. And the numerator is the same. It's going to be that 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, and then try to fit this in. 1.60 times 10 to the minus 19th coulombs squared, and divide by 5.00 times 10 to the minus 9th meters squared. Okay, if I checked my units, this would give me, this part gives me Coulomb squared, which will divide out with those Coulomb squared. I'll have Newton meters squared left on top, divided by meters squared will give me newtons. So that works. F13 in magnitude is equal to 9.21 times 10 to the minus 12th newtons. So a bit smaller than F23 up there. Okay, but I'm supposed to express this force in I hat J hat notation. So this is why I drew this picture really big, because something I can do down here with this picture, well, for one thing, F23, it's easy to see, it just points in the minus J hat direction. So as a vector, F23 will just equal its magnitude, 2.56. It's in the negative y direction, so minus 2.56 times 10 to the minus 11th newtons in the j hat direction, and that minus sign out there will indicate that. But F13 is a little more complicated, but not much. Not if you're happy with right angle trigonometry, and I wish I hadn't written over here, but there will be a component of F13 that points horizontally and one that points vertically. And in this triangle, I've got this angle theta here, which is 36.9 degrees. This horizontal component will equal the hypotenuse times the cosine of that angle, and the vertical component will be the hypotenuse times the vertical component, or times the sine of theta, excuse me. So F23 as a vector will look like this. It'll equal the magnitude of F23 times the cosine of theta in the I hat direction minus the magnitude of F23 times the sine of theta in the j hat direction. And when you plug in the numbers and calculate those things, you'll end up with F23 is equal to, oh, let's see, no, this is F13, excuse me, getting my subscripts mixed up. Okay, F13 as a vector will equal 7.36 times 10 to the minus 12th, whoops, newtons in the I hat direction, minus 5.53 times 10 to the minus 12th newtons in the j hat direction. And so I got that by just calculating these coefficients here. That operation there. And then F23, this is F13 again. F23 I already figured out. It was this expression right here, which I'm going to write with an exponent of 10 to the minus 12th, and it would be minus 25.6 times 10 to the minus 12th newtons in the j hat direction. So you can wrestle with that little transition if you want to, but the net force on this thing in I hat j hat notation I just get by summing these things up, and I'll get F net for this is equal to the 7.36 times 10 to the minus 12th newtons in the I hat direction, and then these two I just add together, and I get minus 3. Oh, yeah, when I add them together, I get about 31 times 10 to the minus 12th, which is 3.11 times 10 to the minus 11th newtons in the j hat direction. So check your math to see that that's actually the sum when you do this. But that's what it looks like. And so that is the net force on P3 due to P1 and P2 expressed in I hat j hat notation. That was a fair amount of work just for 2 charges. Okay, it's not that fun to do. Then, as a last part, I'll calculate the magnitude and direction of the force acting on P3. Well, here's the force. That's my net force. And I can sketch what that thing looks like with its I hat and j hat components. It's actually, if I think of this as 31.1, but anyway, it's got 7.36 times 10 to the minus 12th out here. This is newtons now in the x direction, how many there'll be. 7.36 times 10 to the minus 12th. And the other one that points down here, the other component, is, let's see, magnitude-wise, it's, 31.1 times 10 to the minus 12th newtons, pointing down there like that. So I would expect that when I calculate this net force, I'll get something a bit bigger than 31.1, and I'll take these two things and square them together, and I do. Okay, so for the magnitude of this force, I get 3.20 times 10 to the minus 12th newtons. So that's the magnitude of F net. And the angle looks to me like it's something bigger than 45 degrees here, and I'm just figuring out this thing positively. I'm not worried about a negative angle or anything like that. I'll just put a note on it, measured clockwise from the positive x-axis. And so I calculate this, and I'll call this angle phi instead of theta. So phi is the inverse tangent of the opposite over the adjacent, and actually they both have an exponent at 10 to the minus 12th, which I'm going to ignore because it'll divide out. So I'll say 31.1 over 7.36, and I get 76.8 degrees. And then I just explain which direction it is. Measured clockwise from the positive x-axis. And that gives me a complete description of the force. I know its magnitude, and I know which direction it points. So we'll stop there. Now, the next step in complication, we've dealt with the force due to one charge. We've now dealt with the force due to 2 charges. And we have an expression for, I don't know where I put it, but somewhere around here, we have an expression for multiple charges where you might have a summation. But the next idea to consider is if you have a continuous charge distribution, what will be the force on something? And if you start thinking of things that you did in calculus, how do you deal with continuous distributions? So that'll be a future video.